Today we will start chapter 4, which is about endothermic and exothermic reactions, or the amount of energy involved in reactions, so the change of enthalpy. So what is enthalpy? First of all, enthalpy is represented by the letter H, capital H, and it represents all the energy, kinetic and potential, that atoms have before and or after a reaction. So if we take all our atoms at the beginning of a reaction, before they actually react together, or all our molecules, and we look at the amount of vibration, rotation, translation, and the amount of energy stored in their nuclei and bonds, so all of those energies combined together, as well as the energy involved in the interaction or attraction forces between the molecules or atoms. So if we take all that into consideration, we will call that enthalpy, which again is represented by a capital H. Now, during a reaction, our reactants start with a certain amount of enthalpy, and our products end with a different amount of enthalpy. So that change of enthalpy, or delta H, or also called heat of reaction, will therefore be the difference between what the reactants had and what the products have at the end of the reaction. So this difference, HP for products minus HR for reactants, give me the energy of the reaction, the energy involved in the whole process, whether it's a physical one or a chemical one. Now, we don't want to confuse this with what you learned last year about the bond energies. So the bond energies were only focusing on the bonds themselves, not the energy in the nuclei, and not the energy of vibration, rotation, translation, and whatnot. We were only focusing on the bond energies. So now this year we will focus on everything, actually. So we'll take into consideration the amount of movement, the kinetic energy, as well as the stored energy in our reactants versus our products. And we will learn to calculate the difference between both and understand where it comes from. So if we look at an example here, what we call the standard molar enthalpy change, it is delta H molar. So molar we represent with a little circle here. Actually, I don't know why my font is a little messed up. What it should actually look like should be a little degree sign, but on top, right over here. Sorry, I don't draw very well. So this shouldn't be there. It should be a little circle on top here. So this represents the heat of reaction of 1 mole of a given substance. Again, we want a reference point. So we will always try to compare to 1 mole of a substance within a reaction. What do I mean by this? So let's take a look at this one. So we have a reaction equation here. So we have a hydrocarbon that will burn, that will react with oxygen. So 1 mole of CH3CH2OH. Sorry, this is an alcohol. Never mind. When you have an OH, if you learned last year, when you have an OH group at the end of a molecule that is composed of carbon and hydrogen, this is considered an alcohol. So I have an alcohol that burns in the presence of oxygen to release carbon dioxide and water. So I need 1 mole of this alcohol to react with 3 moles of oxygen, and that releases or creates 2 moles of CO2 and 3 moles of water vapor. Now, the heat of reaction per mole of my alcohol is minus 1,367 kilojoules per mole of that substance. So in other words, every time I have 1 mole of this alcohol that burns, the whole combustion releases this amount of energy. Now, it doesn't mean that I only have 1 mole of this that reacts, or 1 mole of this that's created, and 1 mole of this. No, we say every time that there is 1 mole of this component, this reactant, this amount of energy will be involved, as well as this, and this, of course. Now let's pretend I wanted to express this amount of energy not based on 1 mole of my alcohol, but 1 mole of oxygen instead. Let's pretend I want to focus on the oxygen. So in order to obtain only 1 mole of oxygen, I would have to rewrite my equation, but with 1 mole here. Now you learned last year when you started balancing equations that you have to be consistent all throughout, which means that if I do divide this by 3, I need to divide this by 3, this amount by 3, and this amount by 3. What does it give me? It gives me this equation here. So I now have 1/3 of my alcohol, 1 mole of oxygen, 2/3 of CO2, right? I have 2 divided by 3. And I had 3 moles of water and now have 1. So I'm rewriting the same equation with different coefficients, but basically what I did from here to here is that I divided the whole thing by 3. Now if I do divide the whole line by 3, the whole equation, that means I will also divide this amount of energy by 3, which gives me, this here. So now if I express this amount of energy as a function of oxygen, so for every mole of oxygen that reacts, this is the amount of energy involved. So minus 456 kilojoules of energy is released per mole of oxygen that reacts. I could do the exact same thing based on another substance. So I did the exercise here. If I wanted to express it as a function of carbon dioxide, because my original equation has 2 moles of carbon dioxide, but I want to express this amount of energy as a function of carbon dioxide, I need to divide everything by 2, including the amount of energy involved. So if I have 1 mole of carbon dioxide instead, well, I rearrange or I change my coefficients, right? So everything stays, does make sense, stays consistent, and I will as well divide my energy by 2. So I'm going from 2 moles to 1 mole, which means I now have every time that 1 mole of carbon dioxide is released, this amount of energy is also released through the process. So I can do this with all the substances involved in the reaction, whether it's water vapor, carbon dioxide, oxygen, or the alcohol per se. So I choose one substance as a reference point, and I will express the energy based on that one substance. And again, this here, we have to use the proper symbol. So this represents my delta H molar, so delta, change of enthalpy per mole of a specific substance. In this example here, it's per mole of carbon dioxide. Okay, so lower, you also have the same exercise again, an example for water. If I want to express it as 1 mole of water or per mole of water, because I had 3 as a coefficient here, I will divide the whole thing by 3. So for every mole of water that is formed, this is the amount of energy that was released, along with 2/3 of a mole of carbon dioxide, and I now know that 1 mole of oxygen reacted and 1/3 of a mole of the alcohol also reacted. Okay, so that's how it works with the molar enthalpy. Now that's all that there is really to say for 4.1. 4.1 is just a presentation of what delta H molar is, or what enthalpy or molar enthalpy are. Now we want to get into endothermic and exothermic reactions. So this is unit 4.2. So I'm doing a 2-in-1 in this case. So how do we link the molar enthalpy to an endothermic or an exothermic reaction? Well, first of all, we're going to look at physical changes, how endothermic reactions work with physical changes. So we have a change of state here. We're talking about water. So I have the fusion point or melting point, which is here. And I have the boiling point, which is occurring here. In case you don't already know, when a substance is melting, freezing, boiling, and whatnot, the temperature stays stable until all the molecules have been transformed or have changed state. Now here I have the amount of energy involved in the actual change for water. So every time I have 1 mole of water, it needs 6.01 kilojoules of energy to transform it from solid to liquid. Now, when my liquid starts heating up, it's not changing state, so I don't have an actual reaction, but the water is still stocking some energy. Okay, that's why we call this section Q, right? We talked about Q in the last chapter. We said Q, the amount of energy that a substance absorbs or releases, is based on the mass of the substance, its specific heat, and its change of temperature. So in this case, let's pretend I have 100 grams of water. Well, I'd have 100 grams. I know that a specific heat of water is 4.19. And, oh, actually, let's work with a mole. that would be more intelligent. So 1 mole would be 18 grams. So let's pretend I have 18 grams of water. Specific heat is 4.19 joules per gram degree Celsius. And the change of temperature in this particular case, well, it goes from 0 to 100, right, before it starts boiling. So it would be 100 degrees. That would be the change, variation of temperature. So I could easily calculate how much energy my 18 grams or 1 mole of water absorbed in the whole process. So my solid, depending on at what temperature it starts, will absorb a given amount of energy before it reaches the melting point. During the change, we will talk, instead of Q, we'll talk about delta H because there is an actual reaction or transformation. Then, when the water starts heating up again, the liquid water, we'll talk about Q because it's just stocking energy, but it's not changing state. There's no reaction. Then, when it reaches the boiling point, there is a change of state, so there is a physical reaction. And in this case, it'll involve more energy. It's more difficult to transform a liquid into a gas than to melt a solid. So in this case, for 1 mole or 18 grams of water, my water will require 40.66 kilojoules of energy to transform it into a gas. And then once it's a gas, it can continue to gain some energy and eventually become plasma. So this is for an endothermic physical change. Now, if we look at a chemical reaction instead, there are 2 parts to my chemical reaction, and we talked about that last year. First, we need to take the molecule, give it some energy, break the bonds between the atoms, and at some point we have separated atoms, so they're all loose, so to speak. And then those loose atoms, they form new bonds and they form a new molecule, and that second half of the whole process releases energy. So the bond breaking is really per se endothermic, and the formation of the bonds, the new bonds, is really per se exothermic. But when we talk about an endo or exo reaction, we're looking at the difference between this part of the process and this one. If we look at a different graph, maybe it'll be clearer for you. So let's look at this here. So we have the process of breaking the bonds. There's energy absorbed in that case. So I have my bonds are broken at this point. So I have separated atoms. Now these atoms start reconnecting together, forming new bonds, and that part of the reaction is exothermic. It is the difference between this part and this part that will tell me if the whole reaction, the whole process from start to finish, if it's endo or if it's exo. Clearly in this case there is more energy absorbed than there was energy released during the process, making it a net positive change, so making it an endothermic reaction overall. Another way to look at this would be to look at the difference of enthalpy between the reactants and the products. So if, for example, I have over here, let's pretend I have 20 joules of enthalpy, and here I have 40 joules of enthalpy. Well, the difference between before and after the reaction will give me the overall change of enthalpy during the reaction. So for example, I would have 40 minus 20 is equal to 20 joules that were involved in the reaction, and it was an overall gain. So what you're doing really is delta H of the products, so the enthalpy of the products, minus the delta H of the reactants. If I can make a parallel, it's like saying, how much do I have in my bank account between 2 different months? So maybe in November I have $20, and in December I have $40. So that means overall I deposited more money than I took out. So there's a net increase. Now, if you do the bonds broken minus the bonds formed, or if you do the enthalpy of reactants versus the enthalpy of the products, you will get the exact same value of delta H. So you can use either technique depending on the information given to you. Another way of expressing an endothermic reaction is to express its energy, its enthalpy, change of enthalpy, as a positive value. So if I have my reaction and I want to give the energy involved within the reaction, so this here, the overall energy, of the reaction, I will put a positive value if it is endothermic. The other way I can show it is by putting the energy on the left side. So my reactants need to gain energy in order to be transformed into these products. Yes, energy will be released, as I showed here, during the formation of the new bonds, but overall, because the net change is positive, we will put the energy on the side, on the left side over here. Okay, so those are the different ways we can express or we can show that we have an endothermic reaction, whether it's a physical reaction or a chemical reaction. Now let's take a look at the exothermic physical and chemical changes or reactions. So of course, if I have an exothermic physical change, it will be the opposite of the other one. So my substance is losing energy, so my graph is going downward. The amounts involved will be the same, but of opposite sign. So in this case, my water, my 1 mole of water, is losing this amount of energy, so we will express it as a negative amount. The same way, my Q's will be negative as well, because my water is releasing energy. It's not stocking it anymore. It's not storing it. So because there is a release of energy, I will express the amount as a negative value. If we look at the exothermic chemical change, the same process occurs. I have a molecule, it gains energy, it breaks its bonds, I get separated atoms. These same separated atoms start forming bonds to form a new molecule, and in the process release energy. So the first half is endo. When we break the bonds, it's always endo. And the second half is always exo. But in this case, if we look at the other graph, in this case, the amount of energy absorbed to break the bonds will be smaller than the amount of energy released while the new bonds are being formed. So the net difference between both will be negative, which gives me an exothermic reaction. So if we look at the difference of enthalpy between the reactants and the products to calculate the delta H, we could see, for example, that here we have 20 joules. Let's use the same example as before. And here we have 40 joules. So my reactants are starting with 40 joules. My products end up with 20 joules of energy after the reaction. So if I make the difference between the two values, first of all, visually, it shows, the graph shows that there's a decrease of enthalpy, of energy. If I do delta H of the products minus delta H of the reactants, I will get 20 minus 40, so products minus reactants. That gives me minus 20 joules. So clearly, because my value is negative, it means that I have an exothermic reaction. So during the whole reaction, 20 joules of energy were released. So how do we express this through a thermochemical equation, through a reaction equation? Well, we'll either put the change variation of enthalpy outside the equation and we'll express it with a negative sign to show that the energy is released, or we will put the energy on the product side to show that the overall reaction releases, along with the products, releases a certain amount of energy. Now you'll see here that the number is different. It's because here they're expressing it as per mole of Fe2O3. But since I have 2 moles of Fe2O3, if I'm going to put it within the reaction, I have to be consistent. So I have to put double the amount of energy since I'm releasing 2 moles of Fe2O3. So here they really should have put Fe2O3. It's a little difficult to write with this. There you go. So per mole of Fe2O3, I have this amount of energy. But if I'm going to put it within the reaction, it's important that I take the coefficient into consideration. If I have 2 moles, I need to double this amount of energy before I include it in my reaction equation. So I'm consistent with the law of conservation of matter and therefore the law of conservation of energy as well. So that's it for 4.1, 4.2. Stay tuned for 4.3.